All right, so let me start with the technical points. So first, let me thank the organizers for the opportunity to speak. I'll come back to the in a moment. I should point out that these slides are posted on my website. The URL is there. One reason you might want to look at them during the talk is that the references are all the way at the end. So in case you want to see the reference for any of the things that I'm mentioning, you can find them on the very last slide. Of course, we'll get to that in the end. I should say a little bit about why I'm here, because well, my work doesn't have so much to do with the main themes of this conference. However, I believe, checking real quick to see if any of Munjul's family members have snuck in, I might be the person here who has known Munjul the longest of anybody in this room. So he and I met, we're freshmen at Harvard, starting in 1992. Barry once claims to beat me by a few days. Okay, we're basically tied. So more or less equal with Professor Mazur. I met Munjul when we were both freshmen at Harvard in the fall of 1992. We were both taking the notorious class called Math 55. There were a large number of people from that class in my dorm, in my freshman dorm, so that somehow became the place where the study groups met. So Munjul was coming in quite often from the other side of campus, and since then, we sort of progressed through 4 years at Harvard. In parallel, we were roommates senior year, so I was the one in charge of making sure he got to class on time. I do not promise to do that this week. And ever since then, I've got the opportunity to have a front row seat to his mathematical development, including more or less a literal front row seat back at the ICM. 2014, where I got to sit next to Professor Gross. Watch that. So this story is about something that does involve me in a small way. So that's why I thought it would be appropriate to tell. And as any good lasting piece of mathematics does, it begins with an undergraduate research project. So let me start with that. So I'm going to start with a little bit of mathematics, which I would say is undergraduate level, but in case there are any high school students who here, if you manage to get yourself to a conference at the Fields Institute, then this is probably, you would probably consider this high school level mathematics. So this is a theorem from a paper by somebody named Chen, who I don't really know, in 1995. It covers a number of more classical results and says the following. If you look at functions from the integers from 0 to n minus 1, say, taking values in the integers mod m, and you want to know whether or not such a function is induced by a polynomial. In other words, whether you can compute f by writing down some polynomial, feeding the values 0 through n minus 1 into this polynomial, and then reducing the result mod m. So we want to know about maps that have that form. Now, not every map will necessarily have this form. We'll see on the next slide why there's an obstruction. But first, let me state one of the theorems in this paper, which is that the number of distinct maps that you get this way is this product. As product of, as k goes from 0 to n minus 1, of some divisor of m divided by the GCD of m with k factorial. I wrote it the other way to remind you that this product stops contributing once k gets up to n. I think I can do this. Let's see, here's the magic pointer. So this product is the same because once you get past n, then m of k, once k is big enough, then m divides k factorial, and so the fraction is 1. Okay. So why should something like this be true? Well, the way you see this is you take a general polynomial and write it not in the usual way, but instead of writing it in the usual way as a coefficient times a power of x, I can get the same sort of representation taking any family of polynomials 1 of each degree, right? Because then I can just, well, as long as they're monic. So this is a family here. This is a family of, oops. This is a family of polynomials. This product x through x minus k plus 1 is a family of modic polynomials, one of each degree. So obviously I can represent any polynomial as a sum of these things. Now I write it as an infinite sum just for efficiency, but of course only finitely many terms are non-zero. So it's really a finite sum. These coefficients fk are integers, and this is we're going to be representing most of our polynomials in this talk with this kind of expression. We'll change the products, but we will take advantage heavily of the fact that polynomials can always be represented in terms of any sequence like this. So I represent my general polynomial this way, and then I notice that when I write it this way, the function that this represents, even if I take values in the integers, it only depends on the first n coefficients, because once k gets past n, then one of the product n's, multiple n's, whatever you call them, is x minus n, and so the product will be identically 0 when you plug in that value. So, well, sorry, I guess maybe I said that slightly wrong. Once I get past n, then you have x and x minus 1 through x minus n plus 1 as factors, and so whenever you evaluate one of these things, one of the things in the product is 0. So, great. So the represented function only depends on the first n coefficients, and so it would be enough to verify that the function that's represented by this polynomial is the 0 function if and only if fk is divisible by this ratio. And why is that enough? Because, well, that means that I can get all of the distinct maps simply by running fk from, say, 0 up to this number minus 1. So then I count the product of those sets, and that obviously gives me this product that I've displayed. Great. Okay, so now I get to take advantage of the fact that this representation is still visible over here, and so I can refer to it. So on one hand, if fk is divisible by m over gcd of mk factorial, then when I evaluate this summand, one of these summands at a value x in the range from 0 to n minus 1, then it is forced to be divisible by, well, the product of x through x minus k plus 1 is always divisible by k factorial, and therefore, when I multiply in the fk, by the way I've chosen this fraction, the result is divisible by m. So it vanishes mod f. Okay, so if the divisibility holds, then the represented function is 0. If not, well, let me pick the smallest index such that the divisibility fails, and then I'm going to take that particular value of x and inspect the summands, and I sort them into k less than x, k bigger than x, and k equal to x. For k less than x, I do have the divisibility because I picked out the smallest counterexample. For k bigger than x, I'm just getting 0, as I said before, and for k equals x, I'm getting something not divisible by n. And so one of the basic properties of divisibility is that if you have a bunch of numbers and all of them but one is divisible by something, then the sum will not be divisible by that factor. So that implies the claim. Now, going forward, we mostly want to think of this in terms of a related problem, which dates back to a result of Poya from the early 20th century. He observed that every polynomial with rational coefficients, of course, as I said before, you can obviously write a polynomial in terms of a sequence of polynomials which has one term of each degree. Since I'm now working over Q, I don't have to take the monic, so I'm going to divide out by k factorial to get the so-called binomial polynomial, the polynomial that computes the binomial coefficient of the kth binomial coefficient of the argument up top. So a priori, you get a representation with rational coefficients, and the point is that if you insist on considering polynomials that take integer values on integer inputs, those are precisely the ones where the coefficients in this representation are integers. This is, of course, not true in the standard representation because these binomial things have this property, but their coefficients in the standard power basis are not integers. But if you represent things this way, then this is precisely the guys that take integers to integers are the ones that are integer linear combinations of these things. So the people who think about this on a regular basis sometimes call these a regular basis for the set of polynomials with integer values. That sentence wasn't supposed to come out that way, but it did. Okay. I promised you some necessary condition for a function to be represented by a polynomial. Here's one. So for all integers d dividing m, if a and b are values in this domain which are congruent mod d, then their evaluations should also be congruent mod d. Now, of course, this condition only makes sense when d divides m because the values are in z mod mz, and divisibilities in z mod mz don't really tell you much except for divisors of m. I mean, if you ask for divisibility modulo some other integer, it's the same thing as replacing that with the GCD with m. So this is a necessary condition. One says that such a function is congruence preserving. But one of the observations that's made by Chen in this paper from 1995 is that the converse is not true. So he noticed explicitly if you take n equals m equals 8, then you can write down an example of a function which is congruence preserving but not represented by a polynomial. And if you get lost at some point during the talk, you can try to reconstruct this as a fun exercise. So Chen asked this as a question, for which pairs m and n are all of the congruence preserving functions from 0 through n minus 1 to z mod mz represented by polynomials? Yeah, not one polynomial, of course, one polynomial per function. As I said, this story starts with an undergraduate research project. So for more than 35 years by now, since the late 1970s, Joe Gallion has been operating a summer research program for undergraduates at the University of Minnesota Duluth. In the U.S., these programs are now funded by our National Science Foundation and go under the name of Research Experiences for Undergraduates, or REU. And so Monzo and I both attended this program, not at the same time, but when he went in 1995, this was one of the questions that was set out, and Monzo dispatched this in about 10 minutes. He figured out that if you take the prime factorization of m, then you can detect whether or not every congruence preserving function is represented by a polynomial by comparing the prime factorization of m with n. So if you look at the primes that are less than n over 2, so that's how n factors in. So for each prime less than n over 2, which appears in the factorization, if p is 2, then the exponent should be at most 2, or if p is greater than 2, then, well, this should be less than or equal to 1, because, of course, exponent 0 is certainly allowed and happens most of the time. So the point is that this congruence preserving property gets separated from polynomial functions as soon as the modulus is sufficiently not square free, in some sense. Okay? So now this is one way you can tell the difference between my mathematical style and Munzel's mathematical style. So I was raised doing contest problems like the IMO and so on. And so the lesson I learned from that is when you solve an easy problem, great, you move on to the next, you find a harder problem to work on. Munzel did not come through this system, so the lesson he learned is when you solve an easy problem, great. Is there a harder variant of this same problem that you can solve that will tell you something more interesting? The next part of the story is essentially the content of Munzel's senior thesis. Now, senior theses at Harvard are not generally supposed to consist of original research, but nobody told Munzel that. So Munzel asked himself the question, well, what if instead of considering just functions from this particular set, what if we consider some arbitrary subset of the integers? It helps to distinguish between finite and infinite sets. So I'm going to mostly talk about the infinite case, but it's relatively easy to adapt all this to the finite case, and that was, of course, the original motivation. Can you explicitly describe the set of maps from some set into Z mod MZ, which are represented by polynomials? Now, as we saw, this question is closely related to sort of integer-valued polynomials on certain sets. And this question actually takes place more naturally in a more general framework. So, by this point, we had both studied some algebraic number theory, so we were interested in Dedekind domains. So if we replace Z with the Dedekind domain and Q with its fraction field, so for example, the ring of integers in any number field could be here, or the polynomial ring over a finite field, or finite integral extensions, normal integral extensions thereof. Well, so again, you get a question. If you look at the polynomials with coefficients in the fraction field, which ones map some fixed subset into the ring, into the Dedekind domain? And many special cases of this existed previously, and what Mundell did was essentially to simultaneously generalize all of them by giving a more or less simple recipe for describing, in terms of the set S, which polynomials with k coefficients map S into R. And in the special case where R is a discrete valuation, there's a typo in the writing, but when R is a discrete valuation ring, these polynomials are turn out to be there's a garble here. Well, so let me just say out loud what should have been written on this slide, because apparently it was kind of late last night. When R is a discrete valuation ring, you can describe these polynomials in terms of a special basis along the line of Poyer's observation, and the special basis consists of certain modified versions of the binomial polynomials. We'll see that in a moment. So let me now consider the local case. So R is a discrete valuation ring. So for instance, if I started with the integers, I now take the localization at the ideal generated by some prime number. So I'm only considering one prime at a time here. That makes the story a little bit simpler. So now suppose I have an infinite subset of this discrete valuation ring. So the fundamental combinatorial concept that Mundell introduced to sort of completely solve all the questions in this area is what he calls a p-ordering. I'm writing Gothic p here because that's what I'm calling this maximal ideal. So a p-ordering, which is not quite a permutation of S, but the terminology, never mind about the terminology. It's a sequence of elements of S such that for each value k, for each index k, ak is chosen to minimize the p-adic valuation of the product ak minus 0 through ak minus 1. And for convenience, I'm going to call this the factorial function associated to S, even though it's really the factorial function associated to the sequence. But you'll see it's almost independent of the choice of the sequence. Not quite. Obviously, you can choose such a sequence because you just construct this with some greedy algorithm. You pick A0 to be whatever you want, and then once you've chosen A0 through AK minus 1, you just look at the possible p-adic valuations of this product over all choices of AK in the set. That set is a collection of non-negative integers, so you just pick some element that achieves the minimum value. You have a lot of choice there. This is a very non-canonical construction, but any such construction does the right thing in the following sense, that if you take a polynomial with k coefficients, k being the fraction field of R still, it maps S into R if and only if, when you write it in terms of these sort of generalized binomial polynomials, so you take this numerator to be x minus a naught through x minus ak minus 1, and then you normalize with this thing. So of course this is also the sort of thing you see in the Lagrange interpolation formula. But in this talk I'm going to call it a generalized binomial. So if you use these generalized binomials as your favorite basis of the space of polynomials over k, then the polynomials that map S into R are precisely the ones that have R coefficients, so to speak, integral coefficients in this representation. This is not so hard to prove. I will omit the details. Again, this is something you can try to do as an exercise once you know what the statement is. The interesting part is to come up with the definition. As a corollary, I should mention the following. So the sequence of so-called factorial elements does depend on the choice of the construction, because, for example, if I took S equals R, I could multiply everything by a unit, and that would, of course, change these values, but only by units. However, the ideals that you get, so the ideals that are generated by these elements do not depend on any choices. In other words, the valuation of this thing, even if you made different choices at some early stage, that does not affect the valuations you get at later stages. And this is something you can prove directly in terms of ultrametric geometry without reference to polynomials, but it's not at all straightforward. I wasted a lot of time during my senior year trying to come up with a really, really simple proof of this that didn't go through polynomials. I was able to produce a proof, but I wouldn't call it a simple proof. So So by far the easiest way to see this is to actually prove the statement about representability by polynomials and then go back and deduce it this way. So yeah, you have this slightly mysterious phenomenon that no matter how you make choices along the way, the answers in terms of the valuations of these products come out to be the same. Okay? Okay, so now let me tell you what happens in the global version. Now, in the global version, things are slightly more complicated in general. So I can at least figure out what these ideals are supposed to be. So for each maximal ideal of my Dedekind domain, I can project my set S into the localization of R at this prime, which is a discrete valuation ring. The resulting ideals that I get by doing this construction locally, I can identify those with powers of the ideal P in the original ring, right? Because the ideals in this discrete valuation ring are just indexed by, well, except for the 0 ideal, they're indexed by, I mean, they're all powers of the maximal ideal. So I just take the corresponding power of the ideal in the original ring. Those ideals are almost always the unit ideal. In other words, for any particular K, these ideals, you'll get a product of prime ideals, but most of the exponents are 0. That's not so hard to check. And so what you get is a well-defined finite product of powers of prime ideals. You put that together and define this to be the factorial ideal associated to S. And as I pointed out, this is independent of any choices. This is a completely well-defined thing. And if these ideals happen to all be principal, then you can write down a basis, a regular basis of the set of polynomials that take S into R. So you can construct this good sequence of polynomials, somehow using the Chinese remainder theorem, with the property that a K coefficient polynomial maps S into R if and only if its coefficients in this particular representation are all in R. Typo. If this thing is not principal, so if we're not in the case where all of these ideals are principal, which of course can happen in a general Dedekind domain, then that implies that there is no single sequence like this. Essentially because what all this stuff is telling you is that the possible leading coefficients of polynomials of a given degree that take S into R form a certain fractional ideal, which is the reciprocal of this factorial ideal. And if that's not principal, then you can't write down a generator for it. So you can't find a single leading coefficient that would do the job. So that means that you can't have such a sequence of representing polynomials, but you can still check locally to detect which polynomials take S into R. Okay. Now, even when the ideals are principal, that doesn't mean that these representing polynomials can be written as generalized binomials. That only works if you can find a single sequence that has this p-ordering property for all p at once, all right? So Mudgel calls this a simultaneous p-ordering, but in order to save real estate on my slide, I'm calling it a global p-ordering. These occasionally exist. There are some natural examples where they exist. We'll see 2 of them on the next slide. But most of the time, they don't, even when R is a principal ideal domain. So just because the ideals are principal doesn't mean you can achieve this simultaneous p-ordering condition. For example, a later instance of the Duluth REU had Melanie Wood as a participant. I don't know if Melanie's here yet. I don't remember whether Mudgel or I proposed this problem for the REU. But one of us did. And Melanie proved that if you take the ring of integers in an imaginary quadratic field and take S to be R, so you're looking at the functions, the polynomials with coefficients in the imaginary quadratic field, which take the ring of integers into the ring of integers, then even when that has class number 1, there is no simultaneous p-ordering. You just get obstructions. You get obstructions with small primes happening fairly quickly. So the representing polynomials that you get are not going to be simple products like that, but you can cook them up using, say, the Chinese remainder theorem. Okay, so for example, if you go back to Poya's case, if you take R and S to be just the integers, then the obvious sequence of non-negative numbers is in fact a global p-ordering, and the factorial ideals you get are the usual factorials. So that justifies calling these things generalized factorials. And notice, since I have it here, I can still point. In that case, this expression is the generalized. This generalized binomial is the ordinary binomial polynomial. So that justifies calling this thing a generalized binomial as well. Okay? So one other natural example is if you take the ring of polynomials over a finite field, then you can sort of achieve an ordering in the following way. Well, list the elements of FQ in some order starting with 0, but otherwise arbitrary. And then for every k, write k as a base q numeral, so these digits are in the range from 0 to q minus 1, and use those to pick out elements of the field and use those as the coefficients of a polynomial. So in other words, just translate the base q representation into a base t representation using this indexing. That turns out to be a global p ordering. And this construction reproduces a famous example due to Karlitz, who was more or less the pioneer of the arithmetic of function fields. And so this example was also a case that was studied quite a lot before Mundell. One of Mundell's favorite examples is take the set of primes, because it's sort of an irregular set. It's a pretty easy exercise to show that there is no global p ordering. I think only the primes 2, 3, and one other are involved. But you can still calculate the local p orderings. Hint, start with p itself. That makes it a little bit easier. And you can compute what the things are, what the components are in the factorial ideal, and you get a very simple formula. So, okay. So none of this has to do with p-adic analysis, you might have noticed, and we're quite a bit of the ways into the talk. But that is where the next part of the story goes. So, for something completely different. So what happened after we both graduated from Harvard? Well, we both actually went to Princeton for graduate school, although I didn't stay there very long. But while we were there, we discussed the following topic. So there's this famous result, which was, I guess, some special case of this was proved by Weierstrass, and then it was generalized by Stone in the 1930s. If you take a compact subset of Rn, it's actually more general than this, but let's say a compact subset of Rn, then every continuous function from S to R can be uniformly approximated by polynomials in n variables. Uniformly meaning, right, if you take continuous functions on this set and give them the supremum norm, then you can write this thing as a convergent sum for the supremum norm. Okay. So this is about the time when I was getting very interested in p-adic analysis, which I remain interested in to this day. So I had to work this into the talk somehow. What can I do? So this does have a non-Archimedean analog, which is a famous theorem of Kurt Mahler. Kurt Mahler? Yeah. Not the composer, not Gustav. So if you take n equals 1, then we're just looking at functions from, say, zp to qp, which are continuous. So I'm going to take the compact subset here to be just the ring of integers zp in the p-adic field qp. So what Mahler showed is that every continuous function from zp to qp has a unique representation as an infinite sum of binomial polynomials where the coefficients go to 0. So in other words, the binomial polynomials form an orthogonal basis, even an orthonormal basis, I guess, if you want, for the space of continuous functions from zp to qp. So this is quite a famous theorem. It triggered a lot of work in this area, some of which I'll mention. But you can ask, well, it's relatively easy to generalize this to functions from, well, at least to get an analog of the Stone-Weierstrass approximation theorem for functions from zp to the n to qp. But what if you take inside zp to the n some strange compact subset? So compact meaning just closed and bounded. And what if you replace qb by some other local field? Say the completion of a function field with finite residue field. So is there some generalization of this? Now you might suspect that since I'm seeing the binomial polynomials in here, and we saw the binomial polynomials in Poyer's theorem, that this question should be closely related to questions about integrality, integral values of polynomials. And so it's not so much surprise that this is in fact the case. So this is a theorem that we proved, and it was published in 1997. If you take an arbitrary infinite compact subset of R, again, you can modify this for finite subsets, but it's not so interesting because we already know all the functions on a finite subset can be represented by polynomials exactly. So this is more interesting for an infinite compact subset. Do the same p-ordering construction that we just talked about. So define the sequence by minimizing these valuations of these products. Do the same construction that we did before. Again, consider these generalized binomial polynomials that we were using before in the local case. Then every continuous function has a unique representation as an infinite sum of these things whose coefficients converge to 0. So this is more or less exactly the way you would expect to analogize Mahler's theorem if you replace the ordinary binomial polynomials by Mungel's generalization of them. So this is the sense in which my contribution to this story is rather minimal. At this point, it was sort of obvious how to generalize this, so we just went ahead and did it. I have to say, when I was preparing this talk, I realized that we had missed a corollary in this, and I asked Mungel about this, and he hadn't noticed that this is an immediate corollary either. If you go back and you take a compact subset of k to the n, k is the fraction field of R, this is local field, then it's immediate from this that every continuous function from S to K can be uniformly approximated by polynomials. The reason why it's immediate is, first of all, you can rescale everything into this statement is about subsets of R, but of course, if you start with a compact subset of K, then you can scale it into R. And so there's no harm so you can immediately infer for n equals 1, you can immediately infer this from the previous theorem. In the infinite case, and the finite case is again trivial. But if you want to do this for k to the n, well, k to the n as a k vector space you can identify with some field extension. Just pick some field extension of degree n, encode this function as a continuous function from that field to k, which you can think of as a function to L because k sits inside L. Approximate that in this way, and then disentangle the arithmetic of L into arithmetic over K by just writing everything in terms of a base of K. Well, those will give you continuous functions from K into L, which are polynomials, but you can sort of project from L back down to K. So the analog of the Stone-Weierstrass theorem for non-Archimedean fields, even when you work in vector spaces of arbitrary dimension, is an immediate corollary of this. So if we had thought of this in 1997, we would have put it in the paper. I'm using the fact that every non-Archimedean field has at least one extension of degree n. For instance, if you take a uniformizer and join the nth root, there you go. Yes, this strategy does not apply over R. That's true. I want to mention one thing that is not entirely straightforward about this proof. And this will show up implicitly in the later part of the discussion, but I want to make it explicit in this case because it's easiest to see what's going on in this case. So this theorem, it's not so hard to show that it doesn't depend on the choice of the p-ordering. In other words, if you choose two different p-orderings, you can write the generalized binomial polynomials for one ordering in terms of the other. Of course, the coefficients will be in R because we know Mungel's theorem about representing polynomials is true for both p-orderings. And once you know that, then it's more or less obvious that if you have representations of continuous functions in terms of one of these representations, one of these sequences, then you get them in terms of the other. So there's no real harm in working with a less general class of p-orderings than Mungel originally introduced. And it's actually useful to make a little restriction. So in this paper, we say that a p-ordering is proper. So this has nothing to do with properness in algebraic geometry. It's just we needed an adjective. So for all in M and K, AK is chosen in a new residue class modulo P to the M, i.e. one that doesn't occur earlier in the sequence, if and only if you have no choice in the matter, if and only if you cannot avoid it. So for example, if S is a subset of the integers and you try to take a p ordering that starts like so, where p is some prime, then this is not proper because at this fourth stage, you could have chosen either 2p, which gives you a 2p minus 0 and a 2p minus p. Oh, p is bigger than 2 in this example. So you could have chosen 2p at the stage where I chose it, or I could switch and choose p squared plus 1 because that gives you a congruence of p squared with the 1 and nothing else. So those two are interchangeable, but according to this more precise definition, this example is not allowed because I shouldn't have chosen the new residue class 2p mod p squared because I could have chosen p squared plus 1 in an existing, a previously represented residue class. So I should sort of prioritize for high congruences over many congruences. So, and obviously you can choose your ordering this way. It's just another way. It's just a way of breaking ties in the original definition. And so we get a little lemma that says that if you do this, then you pick up more of the analogy with binomial polynomials. So if you insist on considering these proper p orderings, and you only look at indices where you actually get a new residue class modulo p to the m, then two things being in the set being congruent modulo p to the m implies that their binomial coefficients are congruent mod p. This is a generalization of the classical Lucas lemma on binomial coefficients, which tells you so in the case of the standard p ordering of the integers, every residue class is new, and so this applies for all indices k. And in fact, you can say much more than this congruence, but this is certainly one thing that comes out. And so this shows you that this at least something from the classical arithmetic of binomial coefficients persists in the setting if you're a little bit more careful than Mundell needed to be when he was just trying to establish representations for integer-valued polynomials. Yes?
How would we find a proper p ordering, let's say, if the k term is p to k plus 1? Things like that would.
You mean if the set just consists of those things?
Yeah, if the set just consists of things that you.
Well, as I said, you choose you go to a new residue class if and only if no other option exists. So if you have no option, then you go to the new residue class. So, right, so that there's no, so either, at any given stage, either there is a possibility to choose an old residue class modulo, well, I mean, this is happening for all m at once. So at any given point, what you do is you choose a residue class that's somehow as old as possible. So you choose something that's somehow as congruent as possible to something that you already have.
What if there is no most congruent thing, because there's just like an infinite sequence of increasingly congruent?
Well, you only have finitely many terms preceding, right? So you can't. So nobody can be infinitely congruent, right? If you have finitely many terms preceding a k. So for each one of those, there is some maximum congruence that. Is that right?
I think the key is...
Sorry, yes.
When we're talking about p ordering, we're given like a not through a k minus 1, and we're trying to minimize the valuation of this product a k minus 1.
Yes.
Value. And
okay. Yes. So let me repeat that so in case people couldn't hear. If you sort of try to take things that more and more congruent, then at some point you will fail to minimize the product that has to be minimized, right? Because at least one term of that product will be really, really, really divisible by p. And so once you get up to that point, then you can't possibly be a minimizing choice. So given that you have to be a minimizing choice, which was already in the definition of p ordering, then you can't get into the situation where there's no maximum congruence. Thank you. Okay, so this all represents stuff that happened before 2000. So let me bring this a little bit closer to the present. So sort of the final chapter in this story is what Mundell did with this idea a little bit later, which gets really into more sophisticated concepts of p-adic analysis. So in p-adic analysis, one doesn't just consider continuous functions. Otherwise it would be called p-adic topology or something. We want to do analysis. We want to differentiate things. So we want to consider various notions of differentiability for functions, say, from a local field to itself. So for example, in the representation theory of p-adic groups, and Professor Gross can back me up on this, it's quite often the case that you form a space of functions obeying some differentiability condition, and then you take some sort of topological dual of that and treat that as a space of distributions, and lots of interesting representations of p-adic groups live in those spaces. It's sort of I guess I should also wave to Professor Kedlaya in the back, who spends a lot of, and probably other people in the audience do this a lot. But, so what Mundell showed is that this theorem that we proved on continuous functions can be modified to handle things like continuously differentiable functions of the order and locally analytic functions with a specific order of convergence. However, this is not quite as straightforward as what we did, which is why it took somewhat longer. You have to replace p-orderings by some sort of modified concepts, which are also related to inequality conditions on polynomials. So Mundell, I believe, lectured on this at some conference in 2000 on sort of the germs of these ideas. And then he didn't work on this for a while. There was a PhD thesis written by someone in France in this direction. Finally, Mundell drifted back to this and published a paper in JAMS in 2009 that kind of sets the record completely straight about this. And so this is the last thing that I want to explain. It really illustrates the idea that this combinatorial germ of an idea of considering these orderings on elements subject to minimizing some valuation of a product, this idea is much more flexible than even Mundell realized at the time he came up with it. So, and as I said, I have nothing to do with this story other than being an appreciator of this theorem at this point. So let me first explain the case of continuous differentiability. So for that, I need to go back and talk about another condition on polynomials. So actually on this slide, R is just a domain with fraction field K. I don't need any Dedekind property. So if you have a polynomial over K, then its difference quotient is again a polynomial. Okay? That's straightforward. And you can iterate the construction. The difference quotient, of course, should be thought of as a polynomial in two variables. If you do this R times, you get a polynomial in R plus 1 variables by holding all but the last variable fixed and doing the difference quotient construction on the last variable, same. It's an easy exercise to show that a polynomial over K has coefficients in R if and only if, sorry, this is more trivial than I wanted it to be. This is true, but not very interesting. Maybe I want to say if I evaluate this, maybe the constant coefficients of all of these things. I think that would be enough. Anyway, this is true, but it's not so. I mean, let's just take away the trivial part. If you start with a polynomial with R coefficients, then these things will continue to have R coefficients. So let's just, all I need is the trivial statement, I think. So let me now go back to the local situation where p orderings make sense. So if R is a discrete valuation ring, then we can talk about this modified version of a p ordering, which Mundell calls an R removed p ordering. He calls it that because the minimization condition is that you don't consider the single product, ak minus a0 through ak minus 1. You consider all of the products like that where you remove R of the factors. Okay? So those will have different valuations. You minimize over all of those. In other words, you take the ideal that they generate and you take the valuation of that and you choose AK to minimize that. Okay? That's some ideal. You call it K factorial parenthesis S sub R to keep track of the fact that you have this R removed condition going on. And again, this characterizes some representability condition. This is characterizing the fact that a polynomial has, I don't think this is the right statement. I wrote that all of the differences up to R, up to the kth difference, no. Shoot, this doesn't look like the right formula. So I'm claiming that this characterizes certain polynomial representability, but, oh no, sorry, of course. The right condition is that this thing sends S into R. Sorry, again, it was late. So this thing has the property that it has this, it sends S into R, not just F itself does so, but the difference quotients up to some point do that. So this is some more restrictive condition than sending integers into integers. Maybe I should just write this over here. This might not be visible in the recording, but better than nothing. So the condition that I want is that if you evaluate this difference quotient on sk plus 1, in R, thank you, in capital R, for all indices up to little r. Great. Sorry about that. Yeah, it's basically, the same thing. It's basically saying that f and its first few derivatives. But it's convenient to write it this way when we talk about analytic functions. Now, notice that, again, this means that this ideal is, because it characterizes some representability of polynomials, it's independent of choices. Again, that I dare you to come up with an elementary proof of this. I have no idea. I didn't even try. So this tells you about continuously differentiable functions in the following sense. If I take a local field, K, with valuation ring R, and I take an infinite compact subset, then I'll say that f from S to K is continuously differentiable of order R if the first R difference quotients, starting with the function itself, which are a priori only defined on the elements of SK which have pairwise distinct coordinates. So to speak, this is the complement of the big diagonal. So that difference quotient extends to a continuous function on S to the K plus 1. Sorry, that should be K plus 1. Okay. And what Munzel shows is that the polynomials that we just constructed, when you divide by this factorial, well, you just pick any generator of this ideal. Notice it's not so natural to choose a generator because there are multiple products involved. But anyway, pick some generator of that ideal, use that as the denominator, and then you get a Mahler type criterion for continuous differentiability of order R. The function is continuously differentiable of order R if and only if it has a representation of this form where the coefficients go to 0. And conversely, any such series sums to one of these things. I should have said, whenever I state these theorems, there's an implicit converse that when you write down such a sum, it converges uniformly and has the desired property. Okay? So I will just mention, without giving details, that in the proof it's convenient to reduce to some sort of restricted class of p-orderings. So you have to make a definition similar to the one that I gave in this case, but I don't want to give anything more than the flavor of that, so let me just leave it at that. So there is something like a Lucas lemma that you have to use in the course of this, but the conclusion is manifestly independent of making the definition more restrictive. So this is valid as written. Okay? Okay, so lastly, let me talk about locally analytic functions. So again, let me start with a definition that only refers to integral domains. So if I have an ideal in an integral domain and a subset, then I can say that f is R valued on this subset with a given modulus if I sort of dilate and translate the polynomial, I get something with integer coefficients. Is that right? It's integer coefficients, not integer values, right? So this is a slight misnomer because It's not integer values here. It really is integer coefficients. Okay. Now let me specialize this to the case of a discrete valuation ring. So yet again, these things are represented by generalized binomials using some modified definition of p-ordering. In this case, what you do, this is actually a little bit simpler than the previous one. You choose your a, k to minimize the product you have before, except that you ignore the valuation as soon as it gets past h. So as soon as you get past h, you don't care. So this is somehow much less restrictive in some sense than the original definition. Which makes sense because this is somehow we don't expect to be able to divide by that much because this is a condition on coefficients rather than values past some point. So again, we define the ideal that we get from this product, well, truncated by h. And again, we get a statement that says that f has this representation property if and only if when you write it in terms of this thing, the denominators are bounded by this ideal. So if you take the fractional ideal generated by fk, multiply by this ideal, you get something contained in R. Okay. Is that right? Or do I have another typo in here? Each of these, each term here. Oh, yeah, sorry. I should say, oh, sorry. Yeah, sorry. This is not written correctly. So, right. So I should take the sum of like min of h with the valuation of ak minus ai. Okay, much better. This will teach me to do a slide talk, apparently. I promise I will fix all of these in the posted version later. Okay, so once you get the definition of a p-ordering correct, then you get a representability theorem. And with the same correction, you get a theorem about analytic functions. So if we go back to the local field situation, take an infinite compact subset, then we say that this function is locally analytic of order h, if and only if for each element of my set, when I restrict to the ball of, so to speak, radius p to the h, which is just the translate of a by this ideal, this coset. Of course, that's only defined on the intersection of s with that coset, but I want this to extend to a function on that whole coset, on that whole ball, which is given by a convergent power series. And convergence here, I mean, not in the sense of just it converges when you plug in a value, because that's a little bit too weak, but this is convergence in the sense of the coefficients actually go to 0 at the correct rate. Or in other words, if you take this ball and view it over some large extension of K, like a completed algebraic closure, then you can evaluate it all of the points in that ball. Okay? Yeah, basically any infinite extension would do, right? Yeah, maybe you want it to be, maybe you want an infinite residue field extension. Yeah. I'm not even sure you need that though. I think maybe any infinite extension is enough. Maybe not. Anyway, so Mundell shows that this kind of analyticity condition is again characterized in a Mahler type fashion, using the same sort of p-ordering that I failed to correctly define over here. If you make the definition correct, then this sequence of generalized binomials gives you an orthogonal basis for the locally analytic functions of that prescribed order. So of course this depends, when you say a function is locally analytic, you imply that there's some order. Of course there's no, since the topology is disconnected, it's not like in the complex numbers where being locally analytic actually means analytic. Locally analytic of any given order is a particular condition, and so if you want to consider locally analytic functions, you have to take the union over all h. So you get some kind of locally convex space in the limit. Maybe a Fréchet space or something. No, it's a limit of Fréchet spaces. So this kind of thing generalizes a very important result of Amis, who did this for example, well, she did this, I guess, when S is R for general R, if I remember correctly. And she can do a little bit better than that, but this theorem makes absolutely no condition on S. It's totally general. So If you come along with some strange set that doesn't satisfy a Mises regularity condition, no problem. Okay. That's okay. So the difficulty in general, the difficulty here might be that if S is something very, very strange, it might be difficult to actually calculate a p ordering, or at least calculate what the factorial ideals are. That's certainly a problem, but I was hoping to illustrate with this example of the primes that even if the set is kind of strange, you may have some chance to calculate the factorials as long as sort of the behavior modulo powers of p is not too uncontrolled. Okay, so that's it. Let me just sum up by saying, as I hope to have explained, there is a pretty robust link between integrality properties of polynomials and topological/analytic properties of functions on local fields. And the strategy that Mundell introduced to p-orderings, and I call it not just a definition, but I call it a strategy because, as we've seen, you can modify the definition in various ways to capture various types of integrality properties. But the general strategy provides an approach to dealing with both types of problems in quite striking generality. And it would be interesting to do more than this. For example, I don't know if there are any results about this that get into non-commutative rings, but there are cases that would be quite interesting, like completed group rings of p-adic Lie groups are rings that are non-commutative, but in some sense not too non-commutative, because if you take the commutator of two elements that are very close to the identity, that's somehow much smaller than either of them. So you might hope that you can say similar things in some mildly non-commutative setting. But I haven't really thought about this, so I just leave it as a question and leave you with the references that I promised you at the beginning. Thank you. Yes?
So are there any analogous characterizations of making a bit stronger than locally analytic? Like, for example, can Coleman functions be characterized?
Can you characterize Coleman functions? So things that occur when you take sort of iterated integral, start with a genuine analytic function or a locally analytic function, and then repeatedly do p-adic path integrals. That would be a reasonable thing to try. I don't know if anybody has looked into that, but I would go on a limb and say that I would expect you could do something like this for Coleman functions of a specific order, so functions that occur from, say, k-fold iterated integrals. But I don't think anybody has thought about this, as far as I know. That would be a great direction to try to go with this.
Could Gaudian be recycling this problem in subsequent?
Maybe some of the people who've been to the RU more recently than me than know. Are there other results on p-orderings from the RU? Okay. Maybe it's time to revisit this topic. Yes? In what conditions do you expect to have a simultaneous p-ordering? Is that the question? I don't know other than to say quite rarely. So of course Z has the advantage of having this ordering, its usual ordering that gives you a chance. But so maybe for such nice subsets of Z and maybe FQ bracket T, you might hope that such a thing exists. But we already saw for the primes that if you take a pretty irregular subset of even a nice ring, you don't expect to have a simultaneous p-ordering. So yeah. I think the short answer is that it's very, very rare.